standard language, but I guess we'll see. Okay, so today we are going to talk about bonding. And the first thing I want to remind you of, and this says that you learned this in grade 11. The truth is you learned this in grade 9, the octet rule, which is what we call this basic idea that the first shell holds 2, the next shell holds 8, then 18, and then we said, like, don't think about it. Right? Like we just said, like, run away. Right? And then we like very carefully said, like, never go past calcium, right? And then you just never had to do a Lewis structure that didn't fit in our understanding of how the world worked, right? So like calcium was like the end of the periodic table, right? Because after that, it was just like chaos land. And then even in 11, we started using stuff higher up in the table, but we didn't like talk about how it works, right? Because that would be confusing. Obviously, in this unit, we're going to delve into that side of the periodic table. So in grade 9, you learned about the octet rule, and it stated that stable atoms must have 8 electrons in their valence shell. Again, in the first shell, we said it must have 2, then 8, and then we kind of said, like, who knows? Just leave it alone. But this does comply with what we're learning. It does comply with quantum theory because 8 electrons, or that octet rule, represents full s and p orbitals. And so really quickly, if we talk about magnesium, how many electrons does magnesium have in its valence shell? 2, right? What would its Lewis structure look like? Remember doing Lewis structures? Really? Oh, the Lewis structures aren't bad. I hate the Bohr-Rutherford. Yeah. Yeah, just the dots. So what would this one look like? Yeah, and as a rule of thumb, we usually do like north, south, east, and west. We give them all 1 first, and then we go and pair them up for 2, right? Nobody likes you. Just throwing it out there. So now, should I have not said that? No. I apologize. No, that's fine. I'm going to get fired. You recording this last one? I'm a surgeon. How you doing? Whatever. I've had a good run.
Well, you could edit the video.
You know, I really could.
We have a supplier teacher for like the rest of the semester.
So I don't have a meeting tomorrow. I just figured I'd get fired. All right. So if we were to draw an energy level diagram for magnesium, what would we get? It's got how many electrons total? You can do it either way. Either way. You're going to see this more often. I'm going to show it to you both ways.
Well, why didn't you start showing us this the first time?
Because you're going to see it both ways. I'm sorry that you're going to see it both ways. I wish that in chemistry we only ever showed it to you one way, but we don't. You're going to see it both ways, so I'm going to do it both ways.
You think about it, like going lower to higher?
Yeah. The bottom is low energy. The top is high energy.
It's like the bomb of the page is like high energy. Like low energy.
Yes. Sure. I mean, in as much as it involves using words in the opposite way we normally use them. Okay, so how would this get filled up?
We have up and down arrows for each electron and each shell.
Okay, and how many electrons do I need total for magnesium? 12. So 2, 4, 5, 6, 7, 8, 9, 10. Why did I put them in that order? Exactly. I was making sure that I followed Hund's rule. Very good. And 11 and 12. Okay, so that would be magnesium. And how would I write a short electron configuration for magnesium? Yeah, the shorthand for it. I don't want to write the whole thing.
Like, do you symbol for neon, which is Ne?
Okay, so I'd say neon.
And then you just put 3s.
3s, and how many are in the 3s? Very good. So that'd be the electron configuration for magnesium. Whoa. All right, and what I want to show, well, we'll do one more, then we'll talk about it. What about nitrogen? How many valence electrons in the old sort of octet way of thinking would we say nitrogen had? 5. What would its Lewis structure look like then?
It would look like Ne with 5 total dots on it.
I like everything except I don't like the E. Ne would be neon, right?
Yeah, like that's where they
Yep. So there we go. And if we were to draw an energy level diagram for this, what's it going to look like? Anybody? Okay, how many electrons do I have total? 7. Okay, so I'd fill in 1s. Then I would fill in, that's up to 4. How many more do I need? 1, 2, 3, just like that, right? No, why not? Why not? That's 3. You said I need 3. 7, 2, 4, 5, 6, 7. All right, hey, I already know this stuff. Whatever. I got the marks. That's fine. That's fine.
Is that true?
Oh, everybody's tired of
Are you asking if it's true if I know it or not? I don't even know. No, I do. I do. Sadly, this is what knowing this looks like. All right. And if I wanted to do a shorthand configuration for this, what would I put? Okay, helium. And after that, two S, 2. Anybody?
2p3.
Very good, 2p3. Okay, so there we have it. And in the interest of time constraints, I'm not going to do the third example because I think we can well demonstrate the principle we're looking at here. Valence electrons, what we used to think of as the valence, are really just the electrons in, after the last p orbital. Does that make sense? Or in the case of here, 1s, right? 1s because there is no p orbital. But in other words, what we used to think of as the valence is all the electrons that come after the closest noble gas. Does that make sense? When you make a shorthand configuration, you're looking only at the valence electrons. Does that kind of make sense? I'll encourage you to do the last one, sulfur, for your notes. But keep in mind that shorthand notation wow. All right, well, that was impressive. Shorthand notation shows us the valence electrons. So shorthand notation shows valence electrons, and that's all it shows us. All right, and with this in mind, we can look at different types of bonding. So we know that if there's a large difference in electronegativity between two things, they will form bonds by doing what? Typically, this is metals and nonmetals. Yeah, giving and taking electrons. What kind of bond do we call that? Ionic bonding, good. So for example, if I had magnesium and nitrogen, What's magnesium's Lewis structure look like again? 2 electrons. And if I had nitrogen, what's its Lewis structure look like? What's going to happen here? How are these going to bond? I don't know what that means. Anyone? Come on. Share its electrons? Give them away. So magnesium is going to give nitrogen that electron and that electron. Is magnesium now satisfied? Does it have a full outer shell? Sure. Is nitrogen satisfied? So what do I need? Nitrogen's upset. Nitrogen feels neglected. Yeah, so what do I need? Another magnesium? Okay. Yeah, you're right. So now nitrogen's happy, but now we need another nitrogen. All right. Well, obviously now we can do this. And then what do we need? We need another magnesium. Is this a nightmare? Really? Your nightmares involve physical chemistry that works out perfectly?
It's not working out perfectly.
Are you kidding? Look, there we go.
There's a bunch of robberies.
There we go. So with magnesium with its 2+ charge and nitrogen with its -3 charge when it forms a full bond, this works when we have how many magnesiums? 3. And how many nitrogens? 2. Does that make sense? Yeah.
Why are you using the 100 calculator color?
Because it's awesome. I'm going to be using the rainbow pen a lot, just so you know. If you're wondering how often, the answer is going to be real often.
It's just like a kid that just discovered their new toy as a new trick, and it's just like a new toy.
Correct. Okay, and what we end up with, of course, is 2 nitrogens with full octets. And what charge will they have? They've gained electrons. How many electrons did each of them get? 3, so the charge obviously will be -3. And we will have magnesiums with no electrons in their valence because they've donated them all. And what charge will each of them have? Positive. 2 is correct, because how many electrons has each magnesium given up? 2. And of course, this works as an ionic bond because the total charge is balanced, right? We have -6 in the nitrogens and we have +6 in the magnesiums. That's fairly straightforward, yeah? Sorry? Okay. I'm cool with that. Ionic bonding still works, even in the quantum model, pretty much how we're used to ionic bonding working, which means we're not going to spend a lot of time talking about it because it's not really complicated by this. Basically, atoms will give away electrons until they're what we call isoelectric with the noble gases. In other words, this nitrogen now has an electron configuration of what? It's gained 3 electrons. So its electron configuration will be like neon. And the magnesium has given up its extra electrons, so it now has an electron configuration like, in this case, also neon. So electrically, these are both stable now. Does that make sense? So the nitrogen ion, the nitride ion, is isoelectric with neon. The magnesium ion is isoelectric with neon. Nitrogen has to gain electrons to make that happen. Magnesium has to lose electrons. Does that make sense? Okay. Again, this is not the focus of today's lesson. This has not really changed from how you understood it before. Basically, p orbitals, full p orbital is a comfortable, stable space. That's what we like to know. Covalent bonding, though, is a little bit different. So when differences in electronegativity are lower, we get some kinds of covalent bonding. And covalent bonding happens when atoms do what? Yes, when they share, specifically when they share electrons. Good. So instead of giving and taking electrons, they share them. And so, for example, if we were going to look at chlorine, if we had 2 chlorine atoms, well, how many electrons does chlorine have in its valence? 1 less than argon. And so that's going to be 3s2, and then 3p5 more, right? For a total of 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. And you will note that I have very strategically drawn these with the empty space facing one another. How will they form a bond? Yeah, each will donate an electron to a shared pair of electrons. Oh, it's fun every time. And we actually call this a sigma bond. All right, and for those of you wondering, this symbol is a lowercase Greek sigma. It kind of, if you like, it sort of looks like that. I'm not a very good sigma bond drawer, but there you go.
B rotated 90 degrees.
Now, a sigma bond means that between these 2 atoms, those 2 electrons now orbit both, which means that this chlorine thinks it has 2, 4, 6, 8 electrons in its valence shell, making it happy. And this one has 2, 4, 6, 8 electrons in its valence shell, so it thinks it's happy. So they, well, not just thinks it's happy, they're both stable. As a result, both atoms have 8 electrons orbiting its valence shell. Each of them has 6 unique electrons that orbit only it, and then each of them has this last shared pair that orbits both of them. Does that make sense? Yep. Yeah, you bet. Give me 1 second. So what we're going to do now is look at how do we do this for a more complex compound. And we're going to spend a few days on this. We're going to start with relatively easy stuff. I want to start with carbon dioxide. And the first thing I want you to do is just tell me what is the formula of carbon dioxide. It's right in the name. CO2. And I want you to tell me how many valence electrons this should have all together. I forgot to mention valence, but we're only talking about valence electrons here. It's only the outermost shell of electrons that's involved in these. So count all together between the carbon and the 2 oxygens, how many valence electrons they should have. Take a minute and do that. Yes, ma'am.
Why would you sign it?
Sorry? Because they're
sharing. I use sign
for what?
I was like, here's my plane, it's going that way. And so that way.
Okay, so I would say 61 is 2 octets.
I know, that seems really small.
Okay, 1 second. So we're saying this is straight down. So this is 85 degrees. Okay, and this is 700.
Okay.
So that is 5.
Think of the line individually.
Yeah, and then there's 2.
I was like,
No, forget the ball. Just think of
this is 61 here.
Okay.
Well, I
And
would
then add them
say
together.
if that's 90, that's 85.
Simple way, guys.
This is 5.
More
It's 4 and
complicated.
then
Because you know the hypotenuse, and you're looking.
Come on, dude.
Yeah, but sign
Make it hard.
Come on, bro.
Oh.
You can make it hard, but you have to make it work.
I know.
You got it. You got it. Up top. All right.
Oh, boy.
Does that make sense?
Yeah.
Cool. All right. Okay, so let's talk about this. If we're looking at carbon dioxide, the first thing we're going to need to know before we can make a Lewis structure of it is how many electrons there are altogether. And the answer to that, of course, is that carbon has how many valence electrons? 4. What about oxygen? 6. And of course, how many of these do we have? For a total of? Okay. And when we put the whole thing together then, how many electrons do we get? Okay. So when we go to draw a Lewis structure of a more complex covalent compound, you're going to find that we end up with sometimes interesting and funky arrangements that you couldn't predict. So I'm going to walk you through a process that we're going to use to do this. And it's one of those things that seems tricky at first, and then with a bit of practice, we'll come to you like that. But the first step is to just know how many valence electrons are there, which we've now done. So when we draw this thing, we are going to have 16 electrons. Now, the idea with this is usually there's a middle atom and everything that connects to it. Sometimes you'll have 2 middle atoms connected to each other that everything connects to. In this case, we're going to have 1 middle atom. And the middle atom is usually the least electronegative. So if you look up these on the periodic table, you should know off the top of your head that oxygen is very electronegative. Do you remember that? Oxygen's always an electron hog, right? Like in water, oxygen hogs those electrons from hydrogen. So in this case, carbon is the least electronegative. It's going to go in the middle. If we actually look the number up, carbon's electronegativity is 2.5 and oxygen's is 3.5. So carbon has a much lower electronegativity. It goes in the middle. And then we arrange everything else just around it. Does that make sense? So in this case, there's only 2 other things. I'm going to put them there and there. Oxygens. Now, we know the whole bunch of days we're going to talk about this, we'll talk about covalent bonding. So we know that these things are stuck together, and we know that they're stuck together with what kind of bond? Covalent bond. So we're going to now put a covalent bond between them. And would you always do this in like separate pictures? No, I'm just laying it out this way so we can see the progression when we go and look back. Normally you just work with one picture and keep going. Does that make sense? But so now we have carbon in the middle, oxygen here, oxygen there, and we're going to draw single bonds between them. We do that because we know they have to be bound together. Does that make sense? Carbon dioxide is a covalent bond between carbon and oxygens. Now, and again, this is just a process, but it's a process that works well. All right? The next thing we do is we complete the octets of everything but the middle atom. So put all the electrons that should be around everything, but ignore carbon for now. We always ignore the middle one. So everything should have how many electrons in its outer shell? What's a full outer shell for oxygen? 8. So we are going to top this up to 8. 1, 2, 3, 4, 5, 6. And then this counts as 2, right? So this oxygen now has 8. Does that kind of make sense? What's this oxygen going to look like? The same. 1, 2, 3, 4, 5, 6. And then this counts for 2, so we're up to 8. And at this point, we want to count and see if we have enough electrons. If we do, then we can move on. If we don't, we're going to now top up the middle. But you can only top up the middle if you have more electrons to work with. How many electrons total do we have? 16. Does that make sense? So let's count. 2, 4, 6. What's this count for again? So 8. This counts for bringing us to 10, 12, 14, 16. So do I have any more electrons to give this? Okay, so we are already at 16. So there's no more electrons to give. But is everything happy here? Is this oxygen stable? Well, how many electrons does it have? 2, 4, 6, 8. So is oxygen stable?
Yeah.
Sure. And this oxygen over here is identical, obviously, so it is stable. 2, 4, 6, 8. Does that make sense? What about the carbon in the middle? It only has 4. Is it stable? No. And so here is where we can't add more electrons, right? What I would like to do is say, okay, there we go. Now carbon is stable. The problem is, when these things came together, how many electrons did they have to work with? 16. If I did this, I would now have to have 20 electrons. We can't create electrons out of thin air, so that doesn't work. So if that can't work, what could we do to make this? Well, what if this pair of electrons was shared with carbon? And what if this oxygen also took this pair? Well, so just sharing this pair would now mean carbon would have how many electrons? And so now we could also share this same one, but in nature, again, we said nature's lazy. It is easier for this oxygen to share these electrons than for this one to do double duty and share 2 pairs. Does that make sense? So oxygen will take this pair and share them. And we form what we call double bonds. Now, how am I going to draw the electrons on this oxygen now? How many free electrons does this oxygen have? 4. And we arrange them in 2 pairs, right? So I'm going to draw 1, 2, 3, 4. What about this oxygen over here? The same. Now, I want to mention something, which is if you look up online how to draw Lewis diagrams, you will find 10 different people who teach 10 different methods, okay? There's lots of different ways you can go through the steps and get there. This is the one I've found that will get you the right answer with the most different kinds of things. Is that fair? So it's just an algorithm. It's just a technique to follow. But this is what we end up with. And let's make sure that what we want to check for. 1. Are there 16 electrons? Well, 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 electrons. What's the other thing I want to check for? Yeah, very good. So we're going to check for stability, which in this case means, are there 8 electrons in each valence, right? And so quickly look at this oxygen, 2, 4, 6, 8. It is stable. This carbon, 2, 4, 6, 8. It is stable. And this oxygen, 2, 4, 6, 8. It is also stable. Check. Does that make sense? Okay. One last thing. And I'm going to mention this a bunch of times. So we're going to talk about this lots. But the first bond between carbon and oxygen is what we call a sigma bond. And so this one here would also be a sigma bond. It doesn't matter. I'm saying the top ones were the first ones. You could just as easily say the bottom ones were the first ones. It doesn't matter. Does that make sense? The first bond between any two atoms we call a sigma bond. But the second bond between any two atoms is called a pi bond. In a few days, we'll talk about why these are considered different. The difference between a sigma bond and a pi bond. But the first bond between any two atoms we call a sigma bond, and then any additional bonds after that we call pi bonds. So even if this had been a triple bond, you'd have a sigma bond, and then all the other ones would be pi bonds. Yep.
Just out of curiosity, are there many triple bonds in nature?
It comes up, like nitrogen gas is a triple bond. We can draw a Lewis structure of that after to show why. It comes up. It's less common. If we're going to, and it's actually a great question. Next week, we're going to talk about how you can get multiple different answers, which one's the best one. The rule in nature is always fewer pi bonds is more stable. So if you can make a Lewis structure by having a triple bond, or you can do it this other way by having a single bond and a double bond to different things, it'll always go with the single and double. Pi bonds are energetically less favorable, but they do happen. Is that a useful answer at all? Okay.
In case they get a question, like, which ones are stable?
Yeah, and we'll talk a lot about that. So don't feel like if you didn't pick up that like one-time verbal answer here, we're gonna have a whole lesson about that. Okay. Any questions about that? Yeah. You gotta give me a minute, okay? I will go back up for you in a bit, but we don't have a ton of time, so we'll get there. But I'll work on this next one with you. I want you to try the same thing for the nitrate ion. Nitrate, NO3 with a -1 charge. So this is a covalent compound. So how many electrons total does this thing have? Well, nitrogen has how many electrons in its valence? It has 5 electrons in its valence. Good. What about oxygen? How many electrons does it have in its valence? 6. And how many of them are there? For a total of 18. But then let's not forget, what is the charge of this thing? -1, which means it has 1 more electron than we'd expect it to. Does that make sense? If the thing's going to have a -1 charge, do atoms normally have a charge? No. So if you put a bunch of atoms together and you have a -1 charge, there must be 1 extra electron. Does that make sense? So altogether, how many electrons does that make? 24. Good. Uh-oh. Okay, so nitrogen has 5 electrons in its valence. Oxygen has 6. But there's 3 of them, so 6 times 3 is 18. So you put those together, you get 23. But we're talking about NO3 with a -1 charge. And if it has a -1 charge, that means it has 1 extra electron.
Yeah, I didn't realize it.
No problem. Does that make sense? Great. So 5 from nitrogen, 18 from oxygen, 1 because the thing has a -1 charge, gives you 24.
I just thought you meant 24 oxygen. And that means
Oh, okay. No, yeah, so that's the whole thing. In fact, maybe even I will do this. I will say this is NO3 -1. Okay, now I want you to arrange them. how are these going to be arranged? Well, even if we didn't look at the electronegativity, we have 3 oxygens and 1 nitrogen. What's going in the middle? It's one of the possibilities. Nitrogen, right? But check the electronegativities. Oxygen has an electronegativity of 3.5. Somebody with a periodic table, what's the electronegativity of nitrogen? 3. So oxygen is more electronegative, so the nitrogen goes in the middle. Where should I put the oxygens? Surrounding it. And if we're going to do this neatly, how would you arrange them? I like the fidget spinner idea. Yeah, so we could do that. So that would be kind of like this. Cool. What do I do next? Sorry? Lines between what? Do I do like this?
Yes, that's way cooler than the way you do.
Well, listen.
It's just like a bond.
That's right.
It's a double bond there.
We haven't talked about that kind of bond yet. Have we? Okay, so yeah, we're going to look like this, right? Cool. What do I do next?
Run up to the floor cap here, so I'm going to crack your door open. You can hear my class.
Deal.
In the event that someone does.
Do you want me to rough them up?
Yes.
I'll rough them up real good. Even better.
Only multipliers.
Headlocks for all. Hi, Miss Sargent. Why am I saying these things today? Anyway.
This is fairly,
I'm never like this, right, guys?
fairly mild.
Yeah. I've never threatened physical violence before. I'll hit you if you don't say yes. I did not put any extra vodka in my coffee this morning, thank you. I put only the usual amount of vodka in my coffee. Thank you.
Sometimes you get the extra
Is it like the orange
the
machine?
Monday. Yeah.
I was about to say something cynical, and I'm restraining myself. What do I do next?
I want to hear this.
Nope. What's my next step? Lone pairs. Around what? Okay, so I'm going to do this. And this needs 1, 2, 3, 4, 5, 6, 7, 8 to have 8, right?
No,
Why not?
because bonds are 2.
Because the bonds count as 2. So how many lone pairs does this oxygen need? Yeah, 3 pairs of electrons brings it up to 8. You're going to learn over the course of this that we always think of electrons in pairs, which if you think back to quantum theory makes sense because every orbital ends up being filled with 2 electrons, right? One with an up spin, one with a down spin.
But if it's not full, then it's not.
You're right. But since with a covalent compound, the whole point is sharing to end up with full shells, in this case, they should always be in pairs. Do I have to go rough them up? Okay, and then I have to do this, right?
You're the teacher, you told me.
Maybe.
Okay. I believe here it's, whoa! I believe here it says complete the octets around the surrounding atoms. Okay, here's the deal. We don't know yet if we're going to have lone pairs on the middle atom or if we're going to have double bonds. That's going to depend on how many electrons there are total. Does that make sense? So we can't, other lessons say do that, and then if you have too many electrons, go back. The method I teach is do the surrounding atoms, then pause and count. So let's pause and count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So you tell me, can I do this? Somebody's stopping me. Who's stopping me? The electron police. Because how many do I have? Oh, for God's sake. How many electrons do I have? 24. How many electrons can this compound have? 24. So can I add any? By the way, you will get questions where you have where you have more electrons to work with, in which case you put them on that central atom. In this case, do I have any more electrons? No. So I don't have any more electrons. But does nitrogen need more? All the oxygens are stable. Is nitrogen stable right now? How many more electrons does nitrogen need? All right. Nitrogen needs 2 more electrons. It's a me, electron. So that's how they sound.
They sound like the worst Italian accent ever.
Are you insulting my heritage?
Yes.
My rich Italian heritage. All right, that's one way to do it. So what's going to have to happen here? Very good. So we're going to have to form a new bond, a double bond. How many? If we form 2, then nitrogen would have, like, let's, just for the sake of argument, let's do that. If I did this, how many electrons does nitrogen have now? 2, 4, 6, 8, 10. So we don't want that. How many double bonds does nitrogen want to form? Just 1. Now, as it happens, there's actually 3 different answers to this question.
Oh no.
You can get this one, or you can get this one,
So there's one answer.
or you can get this one. Slow down. So don't write this yet. Don't write this yet. Shh. Those are all different solutions. And before you say, no, they're not the same, no, they're different. Because if you gave those oxygens names, Tim, Robbie, and George, Tim sharing an electron is not the same thing as Robbie sharing an electron, is not the same thing as George sharing an electron. They're different. Well, if they all look alike, never mind. See, that I was going to be cynical again. But the point being, it's not the same thing. It's not the same thing if you're the oxygen that has to share your electrons. Everyone else gets to keep those and you have to share. These are, in fact, 3 different solutions. And this is going to come up in a later lesson. Until we get there, just pick an oxygen and make it the double bond. But I do want to stress that it is going to come up. These are 3 distinct solutions. We call them resonance structures. They're not the same. But because they all have the same outcome, for the purpose of right now, we're going to say just pick one and go.
Why did Tim get smaller when he lost his bond?
I don't know. You'd have to take that up with Tim. So here we go. Now, how many electrons does Tim have on his valence now? He has a pair here and a pair here, and that brings him to 8, right? What about this oxygen? The same? Oh, that's George. Well, you don't even recognize George when you look at him?
He's a plant.
Oh, the triplets.
George has a bit of hair, by the way.
Yeah. I was kind of thinking like a ball cap.
I was thinking of comb over.
Wow. He, there we go. Okay. So there we go. Am I good? I'm done?
No.
Why not?
You didn't draw faces.
So you need.
Yeah, I didn't take these electrons, right? So they're still there. What happened in this case was this pair here gets shared into a bond. Okay. What kind of bond is this? Very good. What kind of bond is that? Okay, if I tell you this was the first bond to form, what kind of bond was this? Sigma bond. Good. And if I tell you that this was the second one to form, what's this? A pi bond. Very good. Don't ask silly questions. Does this look like silly content to you?
Yes.
No.
Does this look like we are being silly?
Yes.
Do you not see the boys over there?
You raise a good point. I'm going to say it's a cherry pi bond. Okay, so that is the process of drawing a Lewis structure. And you're going to see that right now, you could probably intuit some of these. But we will get to complex structures where you really do have to have a process to follow. All right? By the way, we've been talking about the nitrate ion for years. This is what its structure actually looks like. It is, if we draw a Lewis structure of the nitrate ion, it looks like this. By the way, what charge does this whole thing have? Yeah, and so if you remember from Lewis structures, when it has a charge, we draw square brackets around it and we write the charge outside. So that is a full and complete Lewis structure of the nitrate ion. I believe in your homework, you're going to have to do a Lewis structure for the nitrite ion.
You say as you remember.
You should remember. It's not my fault if you don't remember.
You didn't tell us what
Any questions? Okay. Oh, by the way, I didn't tell you. Really? Did I not? Apology accepted. Apology accepted, kids. Okay, and then here I just want to remind that if we were to look at, say, nitrogen gas, or if we look at, oh, I don't know. Well, we'll put the nitrate ion back up. Hey, how many lone pairs would each of these nitrogens have to have? Like that? Well, you tell me. 2, 4, 6, 8. Nitrogen's happy. 2, 4, 6, 8. Cool. The middle bond, the first bond that's formed, what would it be? Sigma bond. What about these other 2 bonds? Pi bonds. Very good. I think we're being whimsical. I'm very whimsical.
Who likes what cherry?
Who likes what? Do you not like cherry pie?
I've never tried it.
Cherry pie, so here's the deal. Good cherry pie is made with cherries that are relatively tart to overpower like all the sugar and like the pectin they use to make it like go together, and it's wonderful. If they make cherry pie from cherries that are too sweet, now it's just like a big sugar bomb, and that's too much for me. But to me, great cherry pie has that contrast between the slight tartness of the sourish cherries and then like the sweet of everything else. And oh, it's real good. It might be among my favorites. I think strawberry rhubarb is my favorite. I don't know. But pumpkin pie. See, blueberry pie is too sweet for me. I cannot eat blueberry pie. It's good for like a bite, and then I'm like, my teeth are going to fall out. Yes. I like it. Okay, what kind of bonds are all these? Sigma bonds. And this last bond here is, of course, a pi bond. All right. Any questions about that? Now listen to me. Look at me. I'm assuming there's 13 of you. I want 26 beady little eyes looking at me. All right. If any of you is missing an eye, I apologize for my insensitivity. We can make that 25. Just give me a second. Do this homework. Email me or come see me if you're not sure how to do a question, because that means you need to help figure it out. Talk to one another. The last couple are even a little tricky. Do this homework. This unit will come at you like a freight train if you don't keep up with your homework. Do the homework.
Haven't we already been in this unit?
Yeah, it's ramping up. Sorry? Listen, when you're in one of your less important classes, like all of them, do this instead.
All of my courses.
Hi, Miss Sargent.